Today, we're diving into the crucial initial steps of any data science project: data collection and preprocessing. These processes truly form the foundational bedrock upon which all successful data science endeavors are built. Let's begin by understanding the three fundamental pillars of data that you will encounter in your work. These are categorized as structured, semi-structured, and unstructured data, each with unique characteristics. First, we have structured data, which is highly organized and easy to manage effectively. This type of data is typically found in defined formats, such as rows and columns in tables. Next, we explore semi-structured data, which offers a balance between organization and flexibility. It possesses some organizational elements, but doesn't strictly adhere to a rigid, predefined schema. Finally, we have unstructured data, which is often rich in content but complex to process. This data lacks a predefined model, yet it contains a vast amount of valuable information. Now, let's talk about data collection, the initial phase of gathering your raw information. This involves employing various methods to gather data efficiently from diverse sources and origins. Following collection, data preprocessing is essential to refine and prepare your datasets. It involves cleaning, transforming, and meticulously organizing the raw data for analysis. Let's delve deeper into the essential characteristics that define structured data and its utility. Understanding these key properties is crucial for working effectively with highly organized data types. Structured data is typically presented in a tabular format, making it easy to read and interpret. Its organized nature means it's easily queryable, allowing for efficient data retrieval and analysis. It also features predefined data types for each column, ensuring consistency and accuracy. This leads to high consistency, which is vital for reliable data processing and insights. Moving on, let's explore semi-structured data, which bridges the gap between structured and unstructured. This type of data is flexible, yet it retains a certain level of inherent organization. First, let's look at the key characteristics that define semi-structured data. A primary characteristic is its lack of a rigid schema, allowing for greater adaptability. It often comes in a flexible format, adapting to evolving data requirements easily. Additionally, semi-structured data is often self-describing, with tags indicating content. Now, let's consider some common examples of semi-structured data you'll frequently encounter. XML files are a classic example, using tags to define elements and attributes. JSON files are another popular example, widely used for data exchange on the web. Even emails, with their headers and body text, represent a form of semi-structured data. Finally, server log files are excellent examples, containing events with varying structures. Let's now explore unstructured data, a common type of data that presents unique challenges and opportunities for analysis. Unstructured data lacks a predefined model or format, but it holds valuable insights like patterns. Specialized tools are required for its analysis. Now, let's delve into the core data collection pillars, which are fundamental methods for gathering information. These pillars are all about effectively gathering valuable insights from a variety of different sources. First, we have primary collection, where data is gathered directly for your specific research needs. Next is secondary collection, which involves using data that has already been collected by others. Web scraping is another pillar, allowing us to extract data from websites programmatically and efficiently. We also collect sensor data, which comes from devices that measure physical quantities in real time. Finally, social media and crowdsourcing provide vast amounts of user-generated data for analysis. Let's compare primary and secondary data, understanding their key differences in collection and usage. This comparison highlights whether data comes from direct observation or from already existing sources. On one side, we have primary data, which is collected firsthand for a specific purpose. Primary data is gathered directly from its original source, ensuring its relevance to your project. Importantly, primary data is tailored precisely to your specific research objectives and questions. On the other hand, Secondary data refers to information that has already been collected. This data has been previously collected by other individuals or organizations for their own purposes. Secondary data is typically accessed from various public or readily available existing sources. Now, let's discuss the crucial process of addressing and handling missing data effectively. The first step is to identify where and how much data is actually missing within your dataset. Next, we assess the pattern of missingness to understand why the data might be absent. Deletion methods involve removing rows or columns with missing values, but this can reduce data. Imputation methods involve filling in missing values using estimated or calculated substitutes. Finally, model integration incorporates missingness directly into your analytical models for robust results. Let's explore some essential feature scaling techniques, crucial for preparing your data for machine learning models. These methods are key to preparing your data, ensuring your models are robust and perform optimally. First, we'll look at min-max scaling, a popular technique for bringing data into a specific range. The formula for min-max scaling calculates x-norm as x minus x-min, divided by x-max minus x-min. Here, x represents your original data point, or feature value that you want to scale. X-min is the smallest value found within that particular feature across your dataset, and X-max is the largest value observed for that same feature in your entire dataset. Finally, X-norm is the resulting normalized value after applying the min-max scaling transformation. This technique scales your data, typically transforming all values to fit within a new range, like 0 to 1. It's especially important when your features have vastly different units or scales, preventing one from dominating. Min-max scaling significantly helps distance-based algorithms, such as k-nearest neighbors, perform much better. Next, we delve into standardization, also known as z-score scaling, another vital technique. The formula for standardization is x standardized equals x minus mu divided by sigma. In this formula, x again represents the original data point or feature value. Mu, symbolized as the Greek letter mu, denotes the mean or average of your feature's values. And sigma, the Greek letter sigma, represents the standard deviation, measuring the spread of your feature's values. X standardized is the resulting transformed value, now with a new scale and distribution. Standardization transforms your data so it has a mean of 0 and a standard deviation of 1. This method is particularly useful when your data approximately follows a Gaussian or normal distribution. Algorithms that assume normally distributed data, like support vector machines, often prefer this scaling method. Let's now summarize the key concepts we've covered regarding data collection and preprocessing. Here are the essential takeaways for effective data preparation, crucial for any successful machine learning project. Remember, understanding different data types is absolutely crucial for effective and appropriate data processing. We've seen that diverse data collection methods exist, each with its own advantages and disadvantages. Missing data and outliers are common challenges that require careful handling to maintain model accuracy. Applying data transformation and scaling techniques significantly improves your model's overall performance. Finally, exploratory data analysis, or EDA, is vital for revealing patterns and guiding your preprocessing steps.